Hello, my name is Naim Majori, and welcome to Lab 2, Motion of a Falling Object. The purpose of this lab is to analyze the motion of a slowly falling object. In this case, I used a crumpled up paper ball that is dropped from rest. Now, the observed motion, which will be collected using Tracker, will be compared to two computational models that is coded in GlowScript. One will consider the effects of the drag force and one won't. And what we should hopefully see is that the model that considers drag force is more closely aligned with the one we got from the Tracker data. And that's because we have air resistance in the real world and we should consider it. Alright, let's talk a bit about the fundamental physics principles used in this lab. First up, we got Newton's second law, which states that a system's change in momentum is proportional to the net force applied. In this lab, we have the paper ball as our system and everything else as the surroundings. And here the surroundings are interacting with our system, with a gravitational force acting downwards and air resistance, or drag, acting upwards. However, we still have a net force pointing downwards, so that means we should expect a change in momentum of our system. Well, what is the gravitational force? It's an attractive force that pulls objects with mass towards each other. Now, in the lab, we have the paper ball and Earth pulling towards each other with equal but opposite magnitude, and that's Newton's third law for you right there. Now, the drag force, this is a resistive force that opposes the motion of an object going through a fluid. And in this lab, the fluid's going to be air. The equation says that the drag force is directly proportional to the velocity of the object squared. And in the lab, initially the paper ball is dropped from rest, so there's zero drag force at rest. And then over time, the drag force is going to increase and increase until we reach a terminal velocity. And that's when the gravitational force balances out with the drag force. All right, so time for the actual experiment. So here's just a quick video of me dropping the ball from rest. There you go. And what we can tell from this is that the initial velocity in all directions is going to be 0 meters per second since it was dropped from rest. Next up, the initial position. This can be collected from the table and graph. And lastly, the change in time from drop to finish was about 0.602 seconds. And all this data will be used in the computational models. All right, so first up, I'm going to make the code for the model that only considers the gravitational force. On the left, I've highlighted all the initial conditions which were collected through the tracker analysis and now are inputted here. B, which is the proportionality constant for the drag force, is initially set to 0 since we're disregarding it in this model. On the right is where I inputted the forces acting on our system, and in this model is just the gravitational force. The velocity update and the position update formula are used for the computer to iterate through the motion of the object so I can graph it. And here's a derivation of both of these. Here's a graph that compares the observed motion of the falling paper ball to that of the computational model that only considers the gravitational force. Now, from zero point 0.4 seconds and beyond, the two curves start to diverge, so this probably tells us that there's another force acting on our system. That extra force is going to be the drag force. So let's create a new computational model that considers both of these forces. The only things I've changed is that the proportionality constant now has a value specified to it. And then the forces, I added the drag force in addition to the weight force. Now here's a visualization of what's going to happen to the velocity and time graph. And as you can see, the velocity graph is now curved instead of being linear like in the previous one. All right, here you go, the final results. This is the graph that considers all three of the different models, the observed and the two computational. And as you can see, the observed model is almost perfectly matched up with the predicted model that considers both the gravitational force and the drag force. What are some possible errors that could have skewed with results? One is outside forces. Since the AC was blowing air out in the room, this could have affected the trajectory of the falling ball. Two is the ball's shape. Since the paper ball was not perfectly spherical, air resistance could have different effects on different parts of the ball. And three is position tracking. The video was recorded at an angle, so this could have had some effects on their proportions and the measurements. Okay, so let's dive a bit deeper into the results. Now, which model predicts a terminal velocity? Well, the model with only gravity shows a linearly increasing velocity in the negative direction. But in contrast, the model accounting for the drag force exhibits non-linear velocity growth. As you can see, it starts to plateau over time, and this kind of predicts that terminal velocity. Next up, what would happen to the terminal velocity if the object was initially thrown downward? Well, it would not change. Terminal velocity is only dependent on the drag force being equal to the gravitational force. So really, the only thing that would change is that the terminal velocity would be reached more quickly. And that wraps up Lab 2. Thank you so much for your attention and have a great day.